three things that we're going to talk about here. We're going to speak about, first of all, is pen working. We'll talk about, first of all, perfect gases. And specifically the perfect gas law, which is something that you need to be familiar with. Some of you will undoubtedly have encountered this already, but it's something that is going to be of critical importance in moving forward and understanding thermodynamics. The perfect gas law is going to be applied a lot, right? Because it's a very good approximation for describing gases. So we'll speak about perfect gases for a little bit. Then we're going to move on and we'll talk a little bit about the kinetic theory of gases. This is a very simple model that we can use to predict properties. Okay, so we're going to think of some very simple, very basic assumptions of how we consider a gas, and then we'll see what follows on from those assumptions. And it turns out that the kinetic theory of gases is a really powerful model that allows us to predict, ultimately will get us back to the perfect gas law. Okay, so we'll see the connection between thinking of gases as small particles that are just bouncing around inside a given volume, and how that leads us to the perfect gas law, and can predict behavior of how pressure and volume and temperature and so on are all related. So we'll speak a little bit about the kinetic theory of gases as well. And then, since, as I just mentioned, the perfect gas is a useful model, it's a useful idealized view of gas behavior, we need to move on to the real world, and most gases are not perfect. The real gases, which means that some of the approximations and assumptions that we make in deriving the perfect gas law won't really work perfectly. So we'll have to deal with what corrections we apply to the perfect gas law to describe real gases. So we've got 3 topics and 3 lectures. The plan is to crank through each one of these topics in each of the lectures. Okay, so first lecture, we're going to talk about perfect gases. On Wednesday, we'll deal with the kinetic theory of gases, and then on Friday, we'll talk about real gases. Okay, so let's start with some background information as we start to worry about what constitutes a perfect gas. Well, to start with, and maybe I've come across some of these ideas before, we need to understand what we mean when we talk about the physical state of a substance. And so the physical state of a substance, and this is going to feed into thermodynamics as well, is going to be determined by its physical properties. And it turns out you don't need to specify too many properties of a bulk system to perfectly or completely specify the state of that system. Specifically, if we want to identify the state of a system, so it's a chemical sample of substance in some container, then we only really need 4 variables to describe that. And those variables are the amount of substance, which gives the symbol N, that is how much stuff do we have, how much material is there present in our system. We need to specify the volume of the system, so I should say, just to highlight the units here, amount of substance gives units of moles. So we measure the amount of substance in moles. We need to specify the volume of the system, ultimately how large our system is, and we specify that in terms of the volume measured in SI units again, with cubic meters. We need to specify the pressure of our system, and this is going to be particularly important when we're talking about gases. We're going to have to think about the pressure that they exert. The SI unit for that is the Pascal. We'll say a little bit more about pressure in just a second. You can break that down into more fundamental SI units. It's a Newton per square meter, which gives you an indication of what the pressure actually corresponds to. So pressure is a force measured in newtons. Per unit area. That is, if we think of a gas contained within some kind of container, the gas exerts a force on the walls of that container. And we'll see when we connect this to molecular theory, that force comes about because molecules, as they buzz around as a gas, collide with the surface of the container. So every time a molecule hits the surface, it bounces off. And as it bounces off, you've changed its momentum. And because you've changed its momentum, you've applied a force. Okay, so that's the force that's going to give rise to the pressure. It's the force per unit area. So pressure is force divided by area. Force in SI units is measured in newtons, areas in square meters. And Newton you can break down a little bit further, because force is also mass times acceleration, which gives it units of overall kilograms per meter per square second of Finally, the last property we need to think about, the last variable we need to define our system is the temperature. And I'll say a little bit more about this later as well. The temperature we're going to measure in absolute temperature units, we'll measure it in Kelvin. Okay, so any equation in which you see temperature applied in thermodynamics in general, you'll need to use the temperature in Kelvin rather than degrees Celsius or Fahrenheit or whatever other units you may be more familiar with for everyday use. For thermodynamics purposes, all of our temperatures are going to be measured in Kelvin. Okay, one more technical point to mention. I'm going to specify or distinguish these variables by classifying them as either extensive variables or intensive variables. An example of an extensive variable would be mass or volume, and an intensive variable would be something like the pressure or the temperature. So this M here corresponds to mass. So what is the difference between an intensive and an extensive variable? Well, an intensive variable, we can imagine if we have our sample, our system that we're interested in containing some substance. If we take a small sample of that system and just look at it to measure one of these properties, say we measure the pressure or the temperature or the volume of the sample that we've collected. Well, if you get the same result regardless of the size of your sample, then you can say that your property is intensive. So an intensive property. So we're going to hypothetically imagine sampling our system and measuring the property. Intensive variables will be, you get the same result basically. That is, if I have a container containing some amount of gas, I grab a small amount of that gas and I measure the temperature. It doesn't matter which part of the gas I collect, I get the same temperature regardless. Similarly, if I measure the pressure in one region of a chamber, the pressure is the same throughout. It doesn't matter which part I sample. But if I measure the mass of substance in that sample, that particular sample, well, it matters how much I've sampled. If I take a small sample, I'll get a small mass. If I measure a larger chunk of the system, I'll get a larger mass, okay? So if the result depends on the magnitude of the sample, or the size of the sample that you take, depends on the amount of substance effectively, then you have an extensive property. That is, it depends on the extent of the sample, is one way to think about that. So extensive properties depend on the sample size, or depend on the amount. So the bigger the sample is, the more mass it's going to have. The bigger the volume I sample, the bigger the volume it's obviously going to have as well. There are intensive versions of the properties like mass and volume that you're probably going to encounter before as well. We can write these in similar ways and call something a molar mass. That is, the molar mass, big M, it's going to be the actual mass in whatever mass units divided by, oops, not that, divided by the number of moles that I sample. Okay, so that's an intensive property. Molar mass, and that will have units of kilograms, again, per mole of substance. Depends on the amount of substance. Similarly, we'll also encounter molar volumes, which is the symbol Vm, which is the volume, again, divided by the number of moles that you happen to have sampled. So the molar volume is also an intensive property, and its units will be meters cubed, again, per mole. So, if we want to define the state of the system, 4 variables, that's what we need. Amount of substance, pressure, temperature, volume. That's all we need to specify the state of our system in thermodynamics. Alright, let's talk a little bit about a couple of these properties in a little bit more detail. So we'll fill this in a little bit more as we go through. Let's talk a little bit about pressure first of all. So as I mentioned, pressure comes around because of collisions between the molecules that make up our system colliding with the walls of whatever our container is. Okay, and the pressure is defined then as the force that's applied by those collisions or resulting from those collisions divided by the area over which they occur. So pressure is force per unit area. So we end up with units here of newtons divided by square meters. Okay, we'll see a little bit more later about how these collisions actually come about exerting this pressure, and what we can infer from a model that includes that. Thermodynamics is often involving relationships to what we call standard states. Okay, it's just a benchmark that we can relate everything to. Standard pressure is defined in thermodynamics with the symbol P with a little circle or a little plimsoll symbol. It's a circle with a line through it. Might see the books looking a bit like that. Despite doing this for several years, I cannot find a suitable little symbol with a line through it in any typeface that I happen to look at, so I just use the little circle. But that means standard state. Okay, so P with the little circle here means standard pressure. And people have made a decision here. We're going to say that standard pressure corresponds to a pressure of 1 bar. Okay, so it's not an SI unit of pressure, but that is what standard state is defined as. And 1 bar of pressure is pretty similar, as you can see in the table here, to what we would consider the atmospheric pressure. It's pretty close to the pressure that you experience day to day at sea level. Okay, so in SI units, it's 101,325 pascals. Sorry, it's atmospheric pressure. A bar is 100,000 pascals. So a bar and an atmosphere, as you can see from the table here, they're actually pretty similar, right? They're only about 1% different. So switching between bars and atmospheres, there's not a great deal of difference between the two. Pascal is actually not a very convenient unit for much of science. Some of SI units often are. But a Pascal, a Newton per square meter, or a kilogram per meter per square second is the SI unit of pressure. What you will also find quite commonly is that people are more than happy to report pressures in a whole range of other units, okay, just for historical reasons mostly. So fairly common units that you will also see used commonly will be the torr, also known as the millimeter of mercury. That is from early pressure measurements. If you have a vacuum and you have a cylinder or a column of mercury, the air pressure down will push the mercury up, so that the two limbs of this U-shaped apparatus have different lengths. Okay, so it's the pressure of air pushing down pushes the mercury up. So you're doing work on the mercury to raise its height. It's still commonly used. So 1 torr corresponds to 1 millimeter of mercury, and so there's 760 of those in an atmosphere, and you can convert between those two. If you're inflating tires on a car or a bicycle, you tend to think pounds per square inch. So 1 atmosphere is around about 15 pounds per square inch. So if you inflate your car with 30 psi, you're putting a pressure of about 2 atmospheres inside the tires of the vehicle. So all of these units are probably going to appear at different points. So it's probably a good idea to be a little bit familiar with how you switch between them. Temperature. We're going to stick to one very specific unit. This is going to be important for where the absolute zero of temperature is, because there's an absolute zero of temperature. And we'll define temperature as defining the direction of energy flow as heat. Okay? And heat is an important thermodynamic concept that I think you'll spend a lot of time talking about later on. But the idea that energy is transferred as heat means that energy flows from regions of high temperature to regions of low temperature. So it's thermal energy, the random motions of the molecules that make up the substance. There's more random motion, more energetic motion, that's a high temperature. And heat is the direction of energy transfer. So heat is a flow of energy, okay? And it's a flow of energy from high temperature, specifically to low temperature. When we're discussing temperatures, we're going to use this thermodynamic temperature scale. As I mentioned, this is going to use units of Kelvin. And Kelvin is defined by setting what's known as the triple point of water equal to some apparently arbitrary number of 273.16 Kelvin. Again, we'll probably hear a little bit more about triple points later, but the triple point of a substance is where the solid the liquid and the gas are all present in equilibrium. So, the solid, and the liquid, and the gas are all present in equilibrium. And that can only happen at a very specific pressure and a very specific temperature. You don't have enough thermodynamic variables to move away from the triple point and maintain three different phases in equilibrium. Okay, so that happens at a specific and fixed pressure and temperature for each substance. And for water, the triple point happens at a temperature is 273.16 Kelvin, or 0.01 degrees Celsius, and at a pressure of about 612 pascals written down, or 6.12 millibar, so thousandths of a bar. Okay, so it's a low pressure and a roundabout freezing. And that's where you're going to have solid, liquid, and gas, all three phases present in equilibrium. Okay, so they are all equally likely to happen at that particular temperature. Any change in temperature or pressure moves you away from that point. Okay. Well, that's our definition of the thermodynamic temperature scale. One quick thing to mention, the way this equation in the red box is written, physical quantities we're going to think of always as being some kind of number multiplied by the unit. Right? This is going to be useful for plugging numbers into equations and so on, plugging values into equations. It's a good idea to keep tabs on the units. I recommend this highly enough. Physical quantities will be a number multiplied by the unit. So if I want to say the temperature is 298 Kelvin, I say that my variable T equals 298 K. I'm used to writing things like that. So what that means is the temperature is 298 times the unit Kelvin. So you can manipulate the Kelvin units algebraically. So T over K is just 298. The temperature divided by the unit Kelvin would be 298. So when you plug numbers into equations, if you're doing plugging values of any of these properties into equations to solve a problem, strongly recommend keeping tabs on the units and making sure that the units cancel out appropriately to get you to the right answer. It's a great check to make sure that you haven't used grams when you should have used kilograms, that you haven't used temperatures in Celsius instead of Kelvin, and so on. So keep tabs on the units. Make sure things cancel out. It's a great way to just check that your number is reasonable at the end. So you can manipulate them just as you would any other piece of algebra. All right. Let's talk about equations of state. So I mentioned there were four variables required to specify the state of the system: the amount of substance, the volume, the pressure, and the temperature. In fact, you don't need to specify four of them. You only need to specify three of them, because the fourth one will be fixed if you know what any three of the other four is. That is, there is an equation of state that relates one property to the other three properties. So for example, we can say that the pressure of our system is some function of the temperature, the volume, and the amount of substance. So it's a function that depends on three variables. But these properties are connected. They're not independent of one another. So P is a mathematical function of T, V, the temperature of the volume, and the amount of substance. And in principle, every substance will have its own equation of state that connects these variables. So there's an equation of state for every substance. The downside is that in general, we don't know them. Right? It's not always clear what those are. There is one where we do know them, or one where we do know what this relationship is, and that's an important example for us. It's an important example for thermodynamics in general. So the equation of state for what we're going to call a perfect gas. And again, a perfect gas here is going to be an approximation of a real gas, but we know exactly what the functional form is that connects the pressure, the temperature, the volume, and the amount of substance for an ideal gas. And it says that the pressure here is equal to the number of moles of substance times the gas constant times the temperature divided by the volume. So this is an equation of state that connects pressure with these other properties. So if I know the other values, Nr, T, and V, then I know what the pressure of the system is, assuming that my gas behaves perfectly. Okay? So the pressure, and just to remind you, in SI units will be in pascals, the amount of substance, in moles, T is the temperature in Kelvin, V here, the volume is in meters cubed, and R is another constant called the gas constant. You're probably familiar with that, having a value of 8.314 joules per Kelvin per mole. So the gas constant, as far as we're concerned, is a fundamental constant. Okay, it's just one of these things that is fixed. It's a fundamental constant. Okay, so I can insert that this is the equation of a perfect gas. P equals nRT over V, PV equals nRT, whichever form you want to look at it in. But it was established ultimately from empirical observations. There was people doing experiments in the lab and seeing how pressure varied with temperature, with volume, and so on in the system. And so various people, several hundred years ago, have worked on this. So we have several basically empirical laws that describe how gases behave that relate some of these thermodynamic variables: pressure, volume, temperature, and amount of substance. So the first of these is Boyle's law, which says that the pressure is inversely proportional to the volume. That is, if I take a fixed amount of gas at a fixed temperature and I decrease the volume of the container, so again, you can imagine this being a gas contained within a piston or something where I can compress the gas. If I decrease the volume, the pressure has to go up. Similarly, if I expand the volume, the pressure correspondingly is going to have to go down as the gas expands. So Boyle's law says that the pressure is inversely proportional to the volume. Or alternatively, I can write this as saying that the pressure times the volume is equal to some constant, provided the amount of gas and the temperature are held constant. Well, you can see from the perfect gas law what that constant is. A little bit of rearranging there says that the pressure times the volume is equal to a constant, which is N times R times T. So these properties are related via this constant. Charles was looking at the relationship between volume and temperature, and he found the volume was directly proportional to temperature. And as if you double the temperature and keep the pressure constant and the amount of substance again constant, then the volume of the system should also double. If you heat up a balloon, it should expand provided the pressure is constant. So if you warm up a balloon or cool down a balloon, again, this is a good example of this. If you take a standard like party balloon, blow it up, dip it in some liquid nitrogen and cool it down to 77 Kelvin, it will completely shrink, right? That is, the volume will decrease at constant pressure, atmospheric pressure, because you've changed the temperature. So volume is proportional to temperature. So volume divided by temperature, again, equals some constant. And in that case, it's the amount of substance times the gas constant divided by the pressure. Gay-Lussac's law, similar trends, pressure is proportional to temperature. You double the temperature. If you keep the volume and the amount of substance constant, then the pressure is going to double. If you halve the temperature, again on a thermodynamic scale, then the pressure is also going down by a factor of 2. And again, pressure divided by temperature here is going to be equal to a similar constant, this time Nr divided by the volume. And then Avogadro's principle just relates the volume to the sheer amount of substance that you have present. You double the amount of gas in your container at fixed pressure and fixed temperature, then the volume also has to increase. Again, blowing up a balloon is a great way to think about that. You blow more air into the balloon, the volume of the balloon is going to increase as you increase the amount of gas put inside the balloon. So volume divided by the amount of substance is in turn going to give me the gas constant times the temperature divided by the pressure. So as long as we're at constant pressure and temperature, that relationship holds. Okay, so we can look at some graphs to see how this sort of behavior we'll see what it actually looks like. So Boyle's law, we know that the pressure times the volume is equal to a constant. We've already seen from the ideal gas law what that is. It's N, the number of moles times the gas gas constant multiplied by the temperature. And so if we plot the pressure against the volume, we get curves that look like this top picture in this slide. And I'll just highlight what we're holding constant. Constant amount of substance, everything I'm going to show you, we'll have a fixed amount of substance. We won't add any or remove any gas from our sample. But here, if we have a constant temperature, we can see how pressure varies with volume. So each one of these lines in this picture, this upper graph here, corresponds to how the pressure varies as a function of the volume if we hold the amount of substance in the temperature constant. So you can see that as you go to lower volume, the pressure has to go up. That is, as you compress your system for the same amount of gas at the same temperature, then the pressure correspondingly increases, and vice versa. If you increase the temperature, you get a different curve. So you can see the arrow pointing there. If you go to increasing temperature, things move outwards away from the axes of this graph as you increase the temperature. So each of these curves are known as isotherms. Okay? And they're called isotherms because that's how pressure varies with volume at a fixed temperature. And at each temperature, you'll get a different isotherm. Okay? So an isotherm means, literally, I guess, iso being the same, therm relating to temperature. So as long as we're at constant temperature, we'll be somewhere along that line. So if you know what temperature your system's at, you know the volume, you know how much substance you have, you know exactly what the pressure should be. It'll be somewhere on that line, on the appropriate line with the appropriate temperature. It's a bit hard to see what's going on or what any trends are from looking at hyperbolas that look like that. So the other way you can look at this is to say, based on Boyle's law again, is that the pressure is proportional to 1 over the volume. If I rearrange my equation, you can see that the pressure is equal to nRT times 1 over the volume. So if I plot pressure against the reciprocal of the volume, I get the bottom graph here, where everything is a straight line, and the gradient is nRT, right? The number of moles of substance times the gas constant multiplied by the temperature. And when you plot it this way, it's pretty easy to see what effect temperature is having on the graph, because temperature is appearing in the gradient. So the bigger the temperature is, the steeper the curve is going to be, okay? The steeper the line is going to be. The other useful thing you can get from plotting the graph this way is that you can see what happens if you extrapolate all the way back to infinite volume. Right? That is, you head back to the origin of the graph. So Boyle's law is an example of what's known as a limiting law. It's true, a good approximation for gases normally, but it's only really true in the limit that the pressure goes all the way to zero. That is, that you head towards zero pressure. So this is what we mean by a limiting law. The good thing for us is that it is a pretty good approximation, even at higher pressures. Okay? And we'll see what sort of things make it a good approximation shortly. So Boyle's law, you can see the pressure is directly proportional. Again, you get a linear graph if you plot pressure against 1 over the volume. So it amounts to the same thing. As for the other ones, well, Charles' law says that the volume is equal to a constant times the temperature. If you plot volume against temperature, according to Charles' law, again, you get a straight line. We can use what we know from the perfect gas law to figure out what that's going to look like. So just a second, the lines that we get here for a volume versus temperature plot are called isobars. Okay? Constant amount of substance. Here, also constant pressure. So an isobar, iso again meaning the same, means constant pressure. So from the ideal gas law, we can see that the volume is equal to N times R divided by the pressure multiplied by the temperature. And once again, the gradient of this graph is now nR over P. So as the pressure gets smaller, the gradient gets steeper for these isobars. Again, another example of a limiting law, only really holds in the limit that you get finally, I just mentioned Gay-Lussac's law as well, because the pressure is equal to constant times the temperature. And if we're holding the other variables constant, the other variables are the amount of substance and the volume. So if we're at constant volume, then we get a line called an isochore. And an isochore again just means constant volume. And the pressure is nR over V multiplied by the temperature. But once again, we get the same sort of behavior. nR over V gives us the gradient. At smaller volumes, we get a steeper isochore, according to Gay-Lussac's law. So we've got three different plots that we can look at here, getting isotherms at constant temperature, isobars at constant pressure, and isochores at constant volume. If we combine these four empirical laws into a single expression, well, we see that PV over NT is equal to a constant, and that constant is the gas constant. And then we have the perfect gas law in familiar form as derived from these empirical observations by holding two of the thermodynamic variables fixed and seeing how the others depend on one another. We see this usual formulation of the perfect gas law. It's PV equals nRT. It's also sometimes referred to as the ideal gas law. The book likes to make a distinction between perfect and ideal, even though they're pretty much synonyms. There is some subtle distinction. I'm in the habit of calling it the ideal gas law, so bear with me if I refer to it as the ideal gas law. It's the same thing I'm talking about. I mean the perfect gas law. Okay. And the perfect gas law is an approximate equation of state for any gas. Okay? It's not exact. It relies on the assumptions that our gas behaves perfectly. And our gas doesn't always behave perfectly. Really, it's an exact law only in this limit that the pressure goes to zero. So it really works only in the limit of very, very low pressures. And it only works in the limit of very low pressures because some of the assumptions that go into this, they're kind of implicit, and we'll get them from the kinetic theory of gases, aren't really true, right? Some of the major assumptions are things like the molecules that make up our gas have no volume, right? That's not true. Molecules are small, but they don't have zero volume, right? They have some finite volume. And it also relies on an assumption that the molecules don't interact with one another beyond collide. We'll see a little bit that that's not true either. Molecules have attractive interactions between them. If they didn't have attractive interactions between them, there would be no liquid or solid state of substances. So there are intermolecular forces that attract them. And so these deviations of finite volumes of molecules, plus the attractive interactions between the molecules at longer range, repulsive at shorter range, cause deviations from the from perfect behavior for most gases. So no gas behaves perfectly, exactly perfectly, but the perfect gas laws are really, for most cases, a very good approximation. You'll see circumstances where it isn't a good approximation a little bit later. And the real test as to whether or not a gas behaves perfectly or not, or how close it is to perfect, is like, well, does this equation work? Right? If it gives you a number that's good enough, then the gas is as good as perfect. Real gases deviate from this law. That is, if you know how much substance you have, R and T, the temperature and the volume, you calculate the pressure, it will deviate from what you predict from perfect behavior. So real gases will give you you'll measure the wrong pressure from what you actually calculate using the perfect gas law. So perfect gases obey this law. Real gases don't. They're going to deviate from the law. The gas constant, just a quick mention of this again in terms of the units. The SI version of the perfect gas law, joules per Kelvin per mole. This is SI units of energy per unit temperature per amount of substance. So this is my SI version. Again, because pressures are often measured in units of atmospheres or bars or torr, or volumes are measured in liters instead of cubic meters. There's a whole range of different versions you'll see from the perfect gas law. Sometimes you might use energies in kcals instead of kilojoules. There's a version of that at the bottom of the table. So you have to make sure that whatever units your other properties are in, you use the appropriate version of the gas constant to match up. One important thing to mention, another constant, fundamental constant that you'll see cropping up at some point is the Boltzmann constant. The gas constant is just the molar version of the Boltzmann constant. So R Boltzmann constant, we'll get the symbol Kb, which is about 1.381 times 10 to the minus 23 joules per Kelvin. Okay, so same units, that's per molecule effectively. Gas constant is per mole, right? So it's often easier to work with the gas constant than the Boltzmann constant, because you can avoid all these huge powers of 10 calculations. So the gas constant, joules per Kelvin per mole, Boltzmann constant, joules per Kelvin, Avogadro's constant as units of per mole. So Boltzmann constant times Avogadro's constant gives you something with joules per Kelvin per mole, which is basically the gas constant. Those are exactly the same, and we'll jump between these two, depending on whatever one is most convenient for us. So we have an equation of state for a perfect gas, right? That is, we're saying that the pressure, one of our thermodynamic variables, is a function of these three other variables that we need to define our system: the temperature, the volume, and the amount of substance. And we've got a functional form for what that looks like. We're saying that the pressure is equal to nRT divided by the amount times gas constant times the temperature divided by the volume. If we fix, again, the amount of substance that we have present, we're not going to change the amount of gas that we have present. So we'll stick with a constant N, constant amount of substance. Then the pressure is just a function of the other two variables. That is, the pressure just the temperature and the volume. So I have a function, two-dimensional function. That is, I have a surface, right? Pressure is a function of temperature and volume. Two variables map out the surface, right? And that surface, you can see in this like three-dimensional plot at the top. I'm plotting pressure as my y-axis against two separate variables, volume and temperature. And the state of my gas has to lie on that surface if the gas behaves perfectly. Okay. So we have a surface of possible states for a fixed amount of gas, and it's somewhere on there, right? So if I pick a temperature and a volume, then I'm somewhere on that surface. Another temperature and a volume, pressure has to be somewhere else on that surface. So we've got this two-dimensional surface that maps out what the pressure is as a function of these other two thermodynamic variables. And you can see, if we start taking slices through this surface, you can return all of the fundamental or basic empirical gas laws that led to its formation. So if I hold the temperature fixed, I have an isotherm. Okay? So you can see the blue part of the graph here. Fixed temperature, I take a slice through the surface, that maps out the isotherm. So that slice through this surface is an isotherm. If I go to a lower temperature, I'm taking a slice through the surface a little bit closer to the front of the graph. I move to a higher temperature, I'm taking a slice through the surface at a slightly further back in the graph. So that's why we get those three separate curves that we saw on the plot: pressure against volume. You can pick out the other versions of this. If we hold different things constant, you can see the isobar. Here, isobar is at constant pressure. So again, that's a slice through the surface at constant pressure. And so if you look down on the top of this graph now, you're basically looking at a plot of volume against temperature, and you can see that the volume increases as the temperature increases. So all of the isobar, isochore, isotherm that we met are these two-dimensional plots. They're all just different slices through the surface as you move one of the other variables fixed. And again, just to reiterate the whole idea, if your gas behaves perfectly, if I know the volume and the temperature, I calculate a pressure. If I hit the surface, which is where it ought to be for a perfect gas, my gas behaves perfectly. If the pressure deviates from that, then the gas is real. Okay, so those are possible states for a perfect gas. Any deviation from the surface indicates real gas behavior, and we need to make some corrections to our picture. Okay, one last thing then before we wrap up this section. We'll talk a little bit about what we do if we're talking about mixtures of gases. So for mixtures of gases, it's going to be useful for us to define for our system. We don't have a single substance present in our container, but we have two or more. We're going to define the mole fraction, which is getting this symbol X of J. So J is just a label to identify some substance. It could be whatever our gas happens to be: argon, helium, nitrogen, right? It's just a label. And so we're going to define our mole fraction as the number of moles of that particular substance divided by the total number of moles of gas that we have present in the container in our reaction vessel. So because the number of moles of that one of J plus the total number of moles is also measured in moles, I can cancel out the units, and the mole fraction is just a number. Okay, it's purely a number. It's a dimensionless, unitless quantity. So X of J here is the mole fraction. It's a unitless quantity. So if a substance contained entirely one substance, X of J equals 1. If it's 50% of that substance, then X of J will be a half, and so on. And the total number of moles is just the sum of the number of moles of each substance that we have present in our substance. So N is the total number of moles. Or total amount of substance. So the sum overall of the all of the mole fractions is also going to ultimately then equal 1. So if I sum up over all of the mole fractions, that equals 1. Just summing up over every possible substance that's present in the system. So we can use this then to define what we're going to call the partial pressure of a gas, if we have a mixture of gases present in our system. And we'll say that the partial pressure of the gas is equal to the mole fraction multiplied by the total pressure that we have present in our system. So each gas exerts partial pressure proportional to its mole fraction. And if you sum up over all of the partial pressures, well, that's going to get me to the total pressure. So however many gases I have, I sum up over all of the individual ones, and that's the total pressure. And this is going to be true for all gases, this definition of the partial pressure. It works for real gases, it works for perfect gases as well. Right? Pressure in total, or the partial pressure is just defined as this mole fraction multiplied by the total pressure. It's kind of similar, but there's a subtle distinction from Dalton's law. So Dalton's law said that the pressure exerted by a mixture of gases is equal to the sum of the pressures that each would exert if it occupied the container or more. It's kind of true. A reasonable approximation works for perfect gases, doesn't work for real gases, because this assumes that there's no interaction again between the gas molecules. So different molecules, I've got molecule A and molecule B present, molecule A and B might interact differently from purely molecules A and purely molecule B. So the partial pressure is not quite the same thing. Dalton's law holds or assumes that the gases behave perfectly. So there's a subtle distinction between these two. But we'll stick with the definition that partial pressure is proportional to the mole fraction and the total pressure that you can measure for the system. I'll stop there because that's pretty much all I was going to say about perfect gases. We'll pick up on Wednesday talking about the kinetic model, which will hopefully lead us back to perfect gases, and then we'll press on with